let's get started. There was, I think, a big issue in one of the questions on the groups of order 96. So the groups of order 96 show that let G be a group of order 96. Show that the following are equivalent. G has no normal subgroups of order 32, and it's equivalent to show that there exists a surjective homomorphism from G to S3. Now, A implies B, I think many of you got, right? But the hard part is A implies B. So B implies A, in my opinion, wasn't supposed to be hard. It was supposed to be the easier one. But the idea is to, I can give you a hint. Look at G modulo the kernel. And that's it. Okay, look at G modulo the kernel and use homework 7, question 1. Okay? So please do that. Yeah.
Was that it for like the surjective homomorphism implies a non-normal subgroup?
Yeah. This is supposed to be way easier than A implies B. You don't need any group actions, anything. Just homomorphisms and isomorphisms. And that's it. Okay, great. Let's do something now. Let's continue with the reading. But before I realized that I had made a small typo or subtypo, more like a mistake. Lecture 25. So please correct this statement. It should be like that. So G acts transitively on a set S with n elements if and only if G has a subgroup of indexing. Even remove set. Remove S on a set with n elements if and only if G is a subgroup of indexing. Okay? Great. Awesome. So let's now continue index n. Okay? Above we say let n be an n. Okay, so again, the level of the questions of the final, you should expect it to be of the same level. Not all the questions, but the tough questions of the final. I don't want to say tough either because I don't think any of them is tough. But you should expect to be of the same level of the group theory homework. Okay? One of them was on your final, so you can expect the same level. Not all of them, of course, but the ones where you have. Anyways, if you're comfortable with the homework, it's a good sign. Okay? Great. Let's continue where we left from rings. So let R be a commutative ring. And I, an ideal. Okay, I think I said verbally that if R is non-commutative, there are things that we call left-sided ideal and right-sided ideal. I didn't say that. I did say that, yeah. Left-sided ideal and right-sided ideal. And we can construct a quotient ring if we have a two-sided ideal, but we will not worry about this in this course. We'll just worry about ideals in a commutative ring. So let R be a commutative ring and I an ideal of R. The set of left cosets. Well, left or right, the set of cosets. R mod I, x plus I, x is in R. Why I don't say left and right cosets? Why do I not say that? I could say left cosets, but why do I not say that? Yeah? R is commutative. And if H is a normal subgroup of G, left and right cosets are actually equal. This is how you can define a group. This set is a ring, is a commutative ring under the following rules. So how do I add two cosets? R1 plus I plus R2 plus I. How do I add these? This is just R1, R1 plus R2 plus I. And then how do I take the product of the two cosets? I take R1 plus I times R1 plus I, R2 plus I, and I get R1, R2 plus I. R1, R2, and I. Last time we saw that these operations are well defined. And what is the identity element for addition here? R1 plus I plus 0 plus I. What is that equal to? This is just equal to R1 plus I. So this is the coset of 0 is the identity element for addition. And what is the identity element for multiplication? It's the coset of 1. Right? We see that? R1 plus I times 1 plus I times 1 plus I is just R1 plus I. 1R plus I. Okay, now from now on I'll start dropping the subscripts R. Okay? I'll just write 1. It will happen more often from now on. Okay? Yes? Pardon me?
The thing behind
Here? You good? Okay. Great. Now, other properties of the operations, associativity of plus times and the distributive law. Follow easily from the properties of. Okay, I'll not do that. You can check this. Multiplication is associative, addition is commutative. I mean, addition is commutative is because it comes from the fact that you have a group. This multiplication is associative. This is just because the multiplication R is associative. It's commutative because multiplication in R is commutative. And R mod I is commutative. It's a commutative ring. Since R1 plus I times R2 plus I is just R1, R2 plus I, which is just R2, R1 plus I. And this is equal to, I'll write it down here. To R2 plus I times R1 plus I. Okay. Okay, great. Let's give an example of a quotient ring. Example, let R be Z and I be NZ for some n. Right? You know that the ideals of Z are in the form NZ. Now what is Z mod I? Z mod I. This is, if n is equal to 0, this is just Z, right? Well, I mean, I don't want to say Z, but as a group, you know it's isomorphic to Z, right? Z mod 0, as a group, you know it's isomorphic to Z, right?
Is it?
Yeah. Z mod 0 is just Z, kind of. Okay? I don't want to say equal. You know, we didn't define isomorphism of rings yet, but you can imagine what it is. Z, and if n is 1, say if n is 0, if n is 1, this is just a 0 ring, or 0. And if n is bigger than 1, this is just Z mod nz, the integers modulo n. Okay? Now I wrote here isomorphic. We didn't really define isomorphisms. We will do today. And you can expect it's almost as the same thing as groups. We just have to add one more operation. Okay, great. Now, Definition. Let R be a ring. A subset S of R is said to be a subring of R if S plus is a subgroup of R plus. Again, the plus should not be written. I mean, it's not necessarily I write it, but it's good. I mean, it's to remind you that always R is a group under addition and not multiplication, unless it's 0. But we're considering that all our rings are non-zero, right? Because we're assuming 1 and 0 are different, unless I specify it like that. Okay? It's a subgroup of R. 1R belongs to S. And then 3, AB belongs to S, implies A times B belongs to S. Okay, so it's a clause under multiplication, contains the identity of multiplication, and is a subgroup of R under addition. So basically, if S is a subring, what does it mean? It means that S is a ring on its own, right? You see that? S is a ring on its own. Yeah. S R is a subring, and only if S is a ring on its own. Okay, because associativity, commutativity, and so on follows from the properties in R, right? Yeah? Yes?
So we don't prove that there is isomorphism as well?
No, it's not. I'm not saying it's a field. Okay? I'm not saying S is field. I'm just saying S is a ring. Okay, I mean, we can here, we're not considered subrings of non-commutative. Okay? Any questions on this? Is Z a subring of Q or not? Is Z a subring of Q? Is Z containing Q? Sorry, just, yeah. And is Z a subring of Q? Is Z a ring? Is Z a ring?
Yes,
Is that under the same operation, kind of the same operation as Q?
pretty much.
Yeah. So Z is a subring of Q. Is Q a subring of R? Is R a ring or not? The real numbers, are they a ring?
Yeah.
Yeah? Are the rational numbers a ring? The product, okay. Is the rational number a subgroup of R? Are the rational numbers a subgroup of R? Add two rational numbers, you get a rational number or not? Yeah. Is 0 in the rational number? Minus a rational number is a rational number. Great. That's done here. Great. Is 1 a rational number? Yeah. Now if A and B are rational numbers, is the product AB a rational number? Yeah. So the rationals are a subring of R. And Z is a subring of Q. Okay. Example. Z is a subring Q. Q is a subring of R. You know, maybe you can see that. If you can't see that right now, that's okay. R is a subring of C. Yeah.
So all we need for S is to be like a subset of R and also a ring for it to be a subring?
Exactly. If you have a ring, then it's a subring of R. If R is a ring, yeah. If it's a ring under the same addition and multiplication in R, not under other rings. Yeah. Just like groups. Okay? Now we'll study ring homomorphisms. Let R and S be rings. A ring homomorphism phi, well, is a function phi from R to S such that what do we expect? So such that phi of R1 plus R2 is equal to phi of R1 plus phi of R2. Okay, so the plus in R means the addition is coming in R being up in R, and the plus in S meaning I'm adding two elements in S. Okay, is that notation clear? It's the same notation as used for groups, right? Yeah. And then phi of R1 times R2 is just phi of R1 times phi of R2, and then I need that phi of 1R is equal to phi of 1S. So a ring homomorphism is just a group homomorphism. Well, it's not just. It is a group homomorphism with additional properties. Right? This is the group homomorphism part, right? You see that? The first part is the group homomorphism part. Yes?
Is it phi of 1s or just 1s?
Oh my god. Thank you. Thank you. Okay? Now definition. Or let's look at some properties. Phi of 0R, what is that equal to? Everybody, phi of 0R is equal to what? 0S. And to, let's see something, phi of minus R is equal to what? To minus phi R, right? Or all R and R. And the proof here is just one line. Why is it one line? Because phi is a group homomorphism, right? And we know this for group homomorphisms. Phi is a group homomorphism from R to S. Okay, great. Now let's define the kernel of a ring homomorphism.
So I have a question.
Yep.
Why do we need to specify phi of 1R is 1S? Isn't that not, is that not like already
No, no,
implied, or?
not necessarily. No, it's not necessarily true. Yeah, it's not necessarily true. This is not true in general. You can find a function that how do you say that satisfies that it's multiplicative but doesn't map the identity to the identity. Okay? Suppose you're assuming rings have no identity, for example. This is how you define a ring homomorphism. Now here we're working with identity, so we're going to assume that the rings have identity. I mean, the idea here is that you want if you have an inverse, you might be able to work your way around that. Just say, okay, one will be mapped to one, but not every element is invertible. Okay? So I mean, yeah, I mean, I can think one of so if you want a ring with identity, so say Z to, well, to Z mod n Z maybe. Z mod 6Z and take x squared equals x, for example. Okay, anyways, I'll try to find an example. I mean, or take everything, map everything to 0, right? If you map everything to 0, this is not satisfied. Okay? map everything to 0, this is not satisfied. I mean, the 0 is a more or less silly example. You can find more interesting examples. Okay? Great. Okay, great. Definition. The kernel of a ring homomorphism phi from R to S is denoted by curve phi and curve phi is equal to R in R such that phi of R is equal to 0s. So basically this is the same as the kernel of the group homomorphism, right? This is just the inverse image of 0s. Okay, what's the next proposition? Phi is injective if and only if what? The kernel is phi from R to S is an injective ring homomorphism. Homomorphism if and only if curve phi kernel of phi is equal to 0 R. How do you prove that? One line. Why is that true? Phi is a group homomorphism, and we know this for groups, right? When is a group homomorphism injective? If and only if its kernel is the identity element of the group. Now phi is also a group homomorphism in this case. So it's injective if and only if the kernel is the identity of the group. And the kernel is just the inverse image of 0, right? Proof follows from the fact that phi from R to S is a group homomorphism. Okay, group here. This is the group homomorphism, not this one. It's the first one. It's the addition. Okay. Should I write this down under addition? Should I mention this, or that's okay? R. You know, it's clear that R and S are groups under addition and not under multiplication. R plus to S plus here S and here R. Okay. Great. First isomorphism theorem, or no, let's do one more. Proposition that phi from R to S be a ring homomorphism. Then kernel of phi is an ideal in R. Here I should mention something. Let R be a commutative ring. Okay, let R be a commutative. Okay, curve phi is an ideal. I just don't want to say it's a two-sided ideal if the ring is not commutative. Curve phi is an ideal in R. Proof. Curve phi is a subgroup of R. Right? Because phi is a group homomorphism. And all I need to check that phi is closed under multiplication by elements in R. So let R be in R. Then X belongs to curve phi. Then phi of Rx. Oops, let me write this here. Let me change A in curve phi. Then phi of R times R in A is just phi of R times in S of phi of A. What is phi of R times phi of A? Phi of A is 0s, right? So this is phi of R multiplied by 0s. This is just 0s. So RA belongs to Are we good? Again, I'm using groups here to show that the kernel is. We know that the kernel is a subgroup of R, right? We know that the kernel is a subgroup, and then I just have to check this property. Okay. Now a small remark. Every ideal, well, I mean, I'll mention it later. Okay, so RA belongs to curve phi. Great. Now, first isomorphism theorem for rings. At phi from R to S. Let R be a commutative ring. And phi from R to S as projective. Surjective ring homomorphism. Then, what can I say? Then R, yes?
What's the difference between kappa and phi?
What is, oh man, I'm reading, oops. Thank you. They're both phi's, right? Are these phi's or not? Yeah, both are phi's, no? Yeah. So, what is this letter? Phi?
It's lowercase phi.
Lowercase phi, and this is uppercase phi. And what is this one?
That's also an uppercase.
Uppercase phi, okay. Great. This is,
It's like
yeah.
it's like an uppercase I. You can
Okay.
just do one bar, you can do the extra zeros.
I see. Okay. So let R be a commutative ring, then phi from R to S is surjective ring homomorphism. Then R modulo the kernel of phi is isomorphic to what? To S. Yeah.
Does it need to be surjective?
Yeah, I mean, otherwise you have to make it surjective. You have to replace S by phi of y. Right? If F is not surjective, you just replace S by phi of R, by the image of R.
But so why don't we do that?
Same. All are equivalent, right? Because in that case, S is phi
Yeah,
of R.
but isn't it more general
No,
to
this
say
is
that
it.
it's just going to be like phi of R without having to be surjective?
But R from phi of R is surjective, right? R from phi of R to phi of R is surjective. Right?
Yeah,
I mean,
it is.
I'll write a remark. I'll write a remark about it. Okay. Remark. Phi from R to S is a ring homomorphism. Then R the kernel of phi is isomorphic to phi of y. Okay? It's the same. It's not different. Because any surjective map, this is just phi of y. Great. Let's prove that. I mean, the proof should be quick. I hope so, at least. Proof. So I will let I denote the kernel of phi. Let I be the kernel of phi. I want to define the homomorphism phi bar from R mod I to phi of R. is S in that case. What is it that equal to? What do you think that should be? S. So you send a quotient R plus I. What do you send it to? To phi of R. Right? Phi of R is well defined. A group isomorphism. Well, phi bar is a group is a well defined and bijective function. Why is that? Why is it well defined and bijective?
Follows from group home.
Follows from group homomorphisms, right? Yeah, you remember that? R mod n. Yeah. Well, please try to review the proof of the first isomorphism for groups. I mean, it's given it's an isomorphism as well, right? Phi bar is an isomorphism and is a group homomorphism, bijective group homomorphism. And it has a well-defined bijective function and is a group homomorphism from R mod I to S. And all we have to check is that phi bar maps the identity of 1 in R mod I, the multiplicative identity in R mod I to the multiplicative identity in S. So let's check that. Phi bar of 1R plus I. What is that? This is just phi of 1 R, which is just 1S. And that is multiplicative. So phi bar of R1 plus I times R2 plus I. This is just phi bar of R1, R2 plus I. This is just phi of R1 of 2. Sorry, I dropped the multiplications. I won't write them every single time. So just phi of R1. Let's write this here. Phi of R2. Let's drop them. Anyways, okay, let's drop them. We'll drop them from now on. Okay? Whenever I have a product, it's in the respective rings. I won't write every single time. Phi of R1 times phi of R2. Great. So which is just phi bar of R1 plus I times phi bar of R2 plus I. So phi bar is a ring homomorphism that is bijective. So phi bar is a ring, is an isomorphism, is a bijective homomorphism. I didn't say what it means to be isomorphic, right? I didn't say what it means. Oh man, is a bijective homomorphism of rings. Okay, note. It is what it is, right? It is what you think. A ring homomorphism phi is said to be an isomorphism if and only if what? It is isomorphism of rings if it is bijective. And what as well? The ring homomorphism is said to be an isomorphism of rings if it's bijective. And what? And we say in that case phi from R to S. In that case, we say that S and R are isomorphic. We say that R and S are isomorphic. it is what it is, right? Like isomorphism, it's a bijective homomorphism. Okay? Then if you have a surjective homomorphism of ring phi from R to S, then R modulo the kernel is isomorphic to S as rings. Are we good here? Are we good? Okay. Another remark. Being isomorphic, what time is it? 10. Okay. Being isomorphic as an equivalence relation on rings. Okay? Okay? Great. 2. Any ideal I of a commutative ring R from U to if ring R is the kernel of a ring homomorphism. Homomorphism. What do I call this ring homomorphism? I'll call it pi bar. Any ideal I, so pi bar. Pi or pi I, what did I call it? Pi I from R to R mod I. R mod I is a ring that sends R to the quotient R plus I. Same thing for groups. Any normal subgroup is the kernel of the canonical projection. Well, any normal subgroup is the kernel of the projection, right? From G to G mod N. Yeah, we're good? We're relying a lot on groups, so please make sure you, but yeah, I mean, if I ask you in the final, prove that a ring homomorphism is injective if and only if the kernel is 0, don't just write, we know this from groups, okay? Okay, don't just write that, so you have to reprove it, or at least prove it for groups and then write it for rings. Yes?
Does it say is the kernel of a ring?
Is the kernel of a ring homomorphism. Kernel. What else? By, oh man, many ways, yeah. Kernel. You know, imagine if we had done rings first, we would have proven these for rings first, everything on its own, then proven these for groups. But now that we have done groups first, we could, you know, go a bit faster on rings and using what we know for groups. Okay. Yeah.
If we did rings before, wouldn't that mean we would say it follows from rings that we can do that?
No, because groups are not necessarily abelian, and right? If we had done rings first, for groups we cannot say it follows from rings, right? Because I is just a subgroup, right? And then you need a normal subgroup if G is not abelian. So, and addition is not multiplicative, so it would be weighted. The operation is not commutative in general groups. Here, the operation is commutative. The group operation is commutative, which is addition. So it wouldn't follow from rings. Okay, great. Let's do an example. Let's do some calculation. Yes?
What's the map from R to R?
R to R mod I. You send a little r to the quotient R plus I.
What's it for?
You just send a little r to the quotient. Okay? You just send G to Gn. If n is normal in G, G to G mod n. Right? Same thing here. Yeah?
So normal subgroups and ideals are like analogs or
Well, so every subgroup of R is a normal subgroup, right? Because R is a commutative group. Okay, now ideals is not, you may be able to find subgroups that are not ideals in general, right? So R, for example, Q, for example. Q has a lot of subgroups, but doesn't have many ideals. Has only 0 and Q, because Q is a field. R has many subgroups, but it doesn't have many ideals, because R is a field. You have 0 and 1. Yeah?
is an ideal just subring?
No. 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 not in our course. Okay? So in our course, ideal. So maybe if you read the book, they define the ideal as a subring. Maybe did they do that? Yeah. So not depends on the conventions they use. In our course, we're using that the facts rings must have a multiplicative identity. Okay. In other textbooks, they don't assume that. You know, it's not a convention that rings have a multiplicative identity. So the way they define an ideal is a subring, for example. Okay, they could define this, but for us, no, it's not a subring. Okay, unless it's the whole ring, right? Unless the ideal is the whole ring, then it's a subring. Okay, because if the ideal contains one, then it contains the whole ring. Okay, we proved this last time. Okay, great. Again, groups are key here. We can. Should we do a small calculation? Let's do a small calculation. Well, a small show that there exists or there doesn't exist any ring homomorphism. Let's work with a nice ring that we will work with a lot, hopefully. Example. Or you know what? Let's do an easy one. Show that there exists no ring homomorphism from Z or from Q to Z. Again, if you look at the book considered a zero to be a ring homomorphism. Okay, this we will not assume it because we need the one gets mapped to one. Great. How do I show that? The idea here is to find an element and find some polynomial relation or find some polynomial equation that it satisfies and see what happens. Let's do something. So if phi is a ring homomorphism, don't try this, this is for us to think. If phi is a ring homomorphism, I want to consider phi of 1/2. What is 2 times phi of 1/2? 2 times phi of 1/2, what is that? What should it be? Phi of? Agree? Because it's a ring homomorphism. It's phi of 1/2 plus phi of 1/2. So phi of 1/2 plus phi of 1/2. This is just phi of 1/2 plus 1/2. What is that? Phi of 1. What is phi of 1? In a ring homomorphism? Yeah, what is it? Exactly. Yeah, Victor? Yeah.
I'm not sure to understand how you can say like 2 times phi of 1/2 equals to phi of 1/2 plus. Is that? Oh.
Yeah. Okay. Is it clear?
Okay, so 2 is not. It's like.
Yeah. Two here is more like an action. Phi of 1. I mean, 2 is in Q as well, right? So it's.
No, yeah, but just that you're doing 2 by saying it's going to be just the thing plus itself.
Yeah.
Instead.
Exactly, because 2 is in Q.
Yeah.
Okay.
I thought you were kind of like inversing phi.
No.
That's.
No.
But you don't know what phi is. You don't.
Yeah, but so if phi is a ring homomorphism from Q to Z, we agree that 2 phi of 1/2 is equal to 1, right? So what is phi of 1/2? 1/2. Can I find an element in Z such that is 1/2 an element in Z? No. Okay, so let's write this down more formally. If phi from Q to Z is a ring homomorphism, then phi, let's write it this way, or phi of 2 times 1/2 minus 1 is equal to 0. Agree or not? This is 1 minus 1, which is phi of 0, is 0. Now what is that? This is just phi of 2 phi of 1 half minus phi of 1 is equal to 0. Well, what is phi of 2? Phi of 2 is just phi of 1 plus 1, right? What is phi of 1 plus 1? Phi of 1 is 1. So phi of 2 is 2. Yeah, very good. 2 phi of 1, 2 phi of 1 half minus 1. Phi of 1 is 1, is equal to 0. Can phi of 1 half be equal to 1 half? Why? Because phi of 1 half is in Z. Phi of 1 half is in Z. So 2 phi of 1 half is different than 1. So no ring homomorphism. From 3 to Z. Yeah.
So the real idea is to say like what we're doing is we're saying since we know that the identity is gonna map to itself,
Yeah.
then we get some kind of like it means that other elements like
Exactly.
map to
So the identity, so any subgroup generated by so all the subgroups, either subgroup generated by the identity will get mapped to itself.
Yeah.
So 1 plus 1 will get mapped to 1 plus 1. 2 plus 2 will get mapped to 2 plus 2. And that's what we're really using. Got it. Yeah.
So we can just say phi of 2 is 2 just because phi of 1 plus 1 is phi of 1 plus phi of 1 is 2.
Yeah. Is that clear? Should I write this down or that's okay? Yeah.
How is that not?
So can you find an element in Z such as when you multiply it by 2 you get 1? 2 times something is always an even integer, say. It can never be equal 1. Okay? No. Phi of 1 half is in Z. 1 half is in Q, but phi of 1 half is in Z. Okay? Great. Now I'll do something here. I'll leave it as an exercise. It's more. How much time do I have? I have like 3 minutes left. Oh, let's do it next time. Maybe I can do one more example here. So I'll do a theorem. I'll leave it as an exercise. I've actually never seen it written in textbooks because more the proof is can be a bit tedious. It's not tedious. It's easy, but not very hard. I'll say it next time. Maybe I'll write down the solution and post it on my courses. I'll write down the proof and post it on my courses. Let's do one question. So let phi is there a ring homomorphism from C to R? Okay, and there's one thing I want to say, or I'll say it tomorrow in the review session. But is there a ring homomorphism from C? Is that a question on your homework or something like that?
Yeah, that is one of the question 7.
Okay, I mean we could do it here. Is there a ring homomorphism from C to R? I mean tomorrow I'll go through the homework, okay? So tomorrow I'll go through the homework. Don't panic, okay? Don't worry.
But tomorrow we don't have
Tomorrow in the exercise session, I'll go through the homework. Okay?
But so is the deadline is there?
The deadline, no, I changed the deadline on Crowdmark. I changed it on Wednesday. It's on Wednesday, right? Yeah. Yes. Yes, of course. Yeah. So is there a ring homomorphism from C to R? Let's try to look at this question. What is the element that makes C weird or nice? I. Why is it weird? Why is it something special? Because I squared is minus 1. Okay, so if I squared is minus 1, can you find a real number whose square is minus 1? No. So let's see where I gets mapped to. If I from C to R is a ring homomorphism, then let's see what phi of I is. What is phi of, okay, so what is phi of minus 1? Phi of minus 1 is equal to what? Of course, right? Now what is phi of I squared? Phi of I squared is minus 1. Agree or not? Because I squared is minus 1. So far so good. Because I squared is minus 1. So you replace that minus 1 by I squared. Right? Now what is phi of I squared? It's just phi of I times phi of I is equal to minus 1. Can you finish it from here? So phi of I is a real number whose squared is minus 1. Is this possible? Is this possible? No. Do we see that? Okay, and then the idea is that our FP is just Z mod PC. I didn't introduce that annotation. But if you want to find a homomorphism from anything, from a ring of this form, or A, B, or Z, where must I go to? I must go to somewhere to a number whose squared is minus 1. Agree or not? Okay, so if you cannot find, if in your ring minus 1 is not a square, then no ring homomorphism exists. Okay? So, yeah, see you all tomorrow. Oh man, I didn't record. Oh, I did. Okay.